Hey, morning. Afternoon. Let's start the lecture. Let's finish this. Let's finish the maximum shear stress theory first, and then we'll get on to the second theory, which is the distortion energy theory. Okay. Yeah. Okay, and we started maximum shear stress theory, and we almost finished that. The theory basically says what you compare is the maximum shear stress in the part. So maximum shear stress, okay, in part, okay, and we use tau max for that indication, and then we compare this value with the shear strengths, okay, so versus the shear strengths. Now the shear strengths in this theory, okay, is based on the yielding point for parts when it's subject to tensile test. Okay, so basically we figured out the shear strengths, okay, under that condition is SSY is the shear strength. It's 1/2, okay, SYT. Okay. So essentially, you're going to compare this with that to see if you're safe or not. All right? Yeah. And this tau max, okay, no matter what, okay, it's always sigma 1 minus 3/2, right? So giving a state of stress, you whether it's a plane stress or 3D stress, so you always look at it in the 3D case. Okay. So you should figure out the sigma 1 and sigma 3, the two principal normal stresses. Then subtract each other divided by 2, you get your maximum shear stress. Okay. So basically, you compare this with this. All right. Yeah. And we also wanted to illustrate is basically graphically how does this MSS theory look like, right? So we had different kind of case number 1 and number 2. I think we already talked about that in the previous lecture. So that's the case when sigma A greater than sigma B greater than 0. Second case is this. Okay, that's the second case. For these two different cases, okay, and for the first case, okay, when sigma A is greater than sigma B and greater than 0, so what we look at is we look at this coordinate system, okay, established by sigma A and a sigma B value. By the way, sigma A, sigma B value, maybe I should write it down here. Sigma A, sigma B value are the two principal normal stresses based on the plane stress, right? Based on the plane stress. Okay. So that's the two sigma A, sigma value. So when it's first case, when it's here, so it's somewhere over here. And when sigma A is greater than the SYT, you have a failure. So basically the safe region is somewhere here. Okay, so this is 45 degrees. So this line here, sigma A equal to sigma B. Okay. Then for the second case, what that referred to is, it's referred to basically the triangles over here. Okay. Yeah. And this value is negative SYT. Okay. And this line at here, okay, this line is sigma A. This line is sigma A minus sigma B equal SYT. Okay. So that's the second, that's the region, safe region for the second case here. Okay, the second case. Okay. And for third case, okay, for third case, it's the case when 0 greater than sigma A greater than sigma B. Okay, that's the third case. So basically, both sigma A and sigma B out of here, okay, they are all less than 0. Okay, they are all negative number. If they are all negative number, so the only location is somewhere here. Okay, somewhere here. Okay. And the safe region. So what you do is, just as the previous two cases, what you do is first nail down which one sigma 1, right? Apparently this sigma 1, which one sigma 2, this sigma 2, and this is sigma 3, right? Sigma 3. Okay. Then according to the MSS theory, we need to get this maximum shear stress. So for the number 3 case, your tau max, right, is sigma 1 minus 3 divided by 2. So that's 0 minus sigma b divided by 2. So negative sigma b over 2, right? That's the tau max in this case. What do we compare with? We compare that with your SSY, which is half SYT, right? We compare this, okay? And when this is greater than that, okay, and this is greater than that, and you have what? Failure, right? You have failure, okay? Yeah. Actually, should I say greater than that or less than that? Yeah, I should still say greater. This is greater. Well, let's look at this thing here, right? Where is this? This is the value. This is the value as. Yeah, that's right. Yeah, we should still say this is greater than that, because in this particular case, okay, sigma b is less than 0. Sigma b is a negative number. Okay, it's a negative number. Yeah. So negative, negative. So this is become positive here, right? Positive. So in terms of this graphical line at here, where is this? So for this particular one here, for this particular one, if you put us equal signs, okay, so that'll be the boundary, right? That'll be the boundary. So equal sign give us the boundary. So what's the boundary here? So the boundary is sigma b, negative sigma b equal SYT, right? This is the boundary. Okay, yeah. And where is it? So that's also sigma b equal negative SYT. Where is it? It's basically this line here, right? Basically this line. Okay, yeah. So anywhere beyond this line over here, that'll be the fading region, and somewhere here, and that's the safe region. Okay, safe region. Okay, yeah. So altogether, 1, 2, 3, that give us this safe region at here. Okay, give us safe region. Okay. Is that good? Yeah. So this is graphical approach, just kind of basically give you a very good idea. Is, see, if you have a plane stress, okay, if you have plane state of stress, and you can immediately calculate, right? You can immediately calculate sigma A and sigma B based on this state of stress, right? And where is that? If you plot that into this coordinate system in here, and you will have an immediate knowledge of whether you are safe or not. Okay, yeah, comparing to this SYT though. Okay, yeah. So that's the application or usefulness of this graphic approach. For aesthetic point of view, basically to make it more beautiful, so what we do is we create the other half of this thing here. Okay, yeah. So that give us this what do we call that? Hexagon, right? 1, 2, 3, 4, 5. Is it called a hexagon? Anyway, it give us this symmetric shape right here. Yeah, it's called hexagon. Yeah. Okay. Yeah. Any questions? All good? Yeah. Now I just want to make one point at here. Okay, just want to make one point here is basically, let's look at a special, what we call special load line. Okay, based on this graph at here. See, in this region or in this quadrant here, there is a special case called pure shear. Okay, so what that means is, at this location here, if you draw a line 45 degree, okay, and which means basically this line is perpendicular to this one here, okay, perpendicular to this. And for this line here, the equation wise, this is sigma b equal to negative sigma a, okay, or sigma a equal to negative sigma b, doesn't matter, okay, yeah. Okay, so this line here, okay, so this line is called the pure shear load line. So what that mean is, if you pick any point on this line here, there's always this relationship between the sigma a and the sigma b. So they are having the absolute value same thing, and they're just opposite of each other, right? Yeah. So this line here, okay, so sigma a equal negative sigma b. This is called a pure shear, okay, load line. Okay, pure shear load line. So let's take a second look at this wording here. So why is it called pure shear load line, right? So the keyword is pure shear. Okay, so if you have a bar of shaft which is under torsion only, that's what we call pure shear, right? Pure shear. So pure shear meaning you have a stress element and there is, okay, no normal stress on it, but only the shear stress. Okay, only the shear stress. See, for example, you have a bar and subjected to a torque only, and if you take any stress element along this cross section here, you get a stress element like this, right? Like this. That's a so-called pure shear. So this pure shear, if I draw the Mohs circle for this stress element, as we learned, so how do I draw the Mohs circle? This is one side, give me 1 point. This is another side, give me 1 point. So this side here, probably a point over here. This side here, probably a point over here, right? So then you create this circle here. Okay, create the circle, right? That's the Mohs circle for this pure shear stress element. Okay, and based on this Mohs circle here, so as you can see now very clearly, when it's under pure shear, what is the relationship between the two principal normal stress? This is sigma A, this is sigma B. Sigma A equal negative sigma B, right? Yeah. So that's why this line here is called pure shear load line. Okay, pure shear load line. Okay. Now, why is it pure shear is an important thing to wanting to point it out? Well, it's just like a pure tensile test, right? When you do tensile test, what important data you obtained? You do a tensile test on a test specimen, you obtain this very important number for that material, which is yield strength, right? Yield strength. So that's yield strength. Now, if I want you to obtain, can you do an experiment to give me the shear strength, or so-called yield strength in shear? So what would you do? Are you still going to do the tensile? Probably not. What are you going to do? You're probably going to do a this test, right? They call it basically torsional test now, right? Torsional test. So the torsional test will give us the shear strength. Okay? Yeah. So this torsional test give us this SSY. Okay. Now, however, right, torsional test usually not as easy to carry out as a tensile test, though, right? Yeah. And what does torsional test give us? Torsional test give us exactly this pure shear load condition. Okay, that's what happens here. Okay. Yeah. Okay. So now coming back here, we know what SSY is. We know our SSY here. We know it's half SYT, right? We know this is SYT. Okay. So I probably should be careful here. SSY. In this particular case, for MSS, we give a number which is 1/2 SYT here, right? But however, you got to be careful is this doesn't mean that every material have a shear strength is this. Okay, you know, you do experiment, you're gonna get a different number. And this value here, 1/2 SYT, that's just the value based on the MSS theory. Okay, MS theory. As I'm gonna point it out, the next one, the distortional energy theory, we're gonna get a slightly different SSY. Okay, with another theory. Okay, yeah. So essentially, the theory based on the value, and experiment will probably give you another close value, or maybe a very different one, but it will be close to this. Okay, yeah. So coming back here, what will be the intersection between this line and this line at here, right? This intersection point. Okay. Why this intersection point is important? Because what does this line here mean? This line means this is a safe region, right? Safe boundary. Any point outside here is unsafe, and any point within here is good. So if you have a loading condition, if you have a load line, you have a point moving, changing along this pure shear. So basically, it's like you're doing this torsional test. You're increasing the torque, right? So then your loading condition will change. So up to where? Maybe when your torque is increased up to this point, and that's the fading point, right? That's the fading point. Start to see the fading point. So the intersection point here, basically, that's an important point. And how you can easily solve, right, two equations. One, this line equation, and the other is this line equation. What's this line equation here, right? What the other line equation is this, okay? So find the intersectional point between these two lines. Okay, it's very easy. Okay, so you can, if you solve this one here, essentially, if you solve this sigma A equal to negative B, and the other one sigma A minus B equal to SYT, and you will see that the sigma A equal to SYT over 2. Okay, so we have T store 2. Yeah. So sigma A here is SYT over 2. So which means what? When you're doing the torsional test, okay, when you're doing torsional test, according to this MSS theory, okay, MSS theory, when your principal normal stress sigma A reach this point, you about to have the failure, right? About to have the failure. And at this point, what is the tau max? Tau max is the same magnitude as sigma A, which basically means tau max is SYT over 2, right? That's exactly what this MSS theory has been telling us here, all right? Yeah. Okay. So that pure shear load line is a special case over there. Okay, it's a special case. Okay. Any questions? Yeah. So that basically concludes this MSS theory. Okay, so we'll look at examples shortly, but that's essentially the theory here. So later, when we're going to apply this MSS theory for static loading, okay, the typical application, what we do is there are two ways. Basically, one is analysis, the other way is design. For analysis, okay, and it's basically you're trying to calculate based on the safety factor. So what do you compare? You compare this SSY with the tau max. Okay, so you look at the safety factor. So this is the K equation. Okay. Yeah. Okay, so this is MSS. Now let's look at the second theory, distortion energy theory. The second one is a more useful theory, though. Okay, in my point of view. So what we call is the DE theory. Okay, second one is more useful, or more applicable in many situations. So let me start with another observation first, then we'll write down the definition of this distortion energy theory. All right? Yeah. So let's say I have a certain parts of whatever. Okay. Now the part will be subjected to certain loading. Okay. Yeah. Now I'm gonna take a stress element out of the part. Okay, out of the part. So it's a 3D, right? And basically there will be certain kind of loadings, okay, maybe on each side of this element here. Okay. So now here's an observation people noticed during experiment. Okay, during experiment, when you subject this ductile material, hydrostatically, or basically when you stress it, okay, hydrostatically. So what I'll explain what it means here. Okay, so when you stress that, okay, so this is the wording, okay, hydro, okay, statically, okay. So the hydrostatic really means is you apply even, okay, kind of stress on each side of the cube, even, basically all the same, okay. So every side can feel, let's say, 3 megapascal or something like that, the pressure, right, or stress, okay. That's what we call hydrostatically. Okay? And non-hydrostatically essentially means each side feels different, okay, feels different. So when you stress this hydrostatically, what people notice is this material or this part will tend to yield at a much higher yield strength, okay, than the part that's subjected to non-hydrostatic stress. Okay. So in other words, essentially you evenly stress that part or load the parts, press the part, okay, or compress it or stretch it, okay, the parts will tend to feel at a much higher yield strength than a part that is subjected to uneven stress. Okay. So for example, you have a steel or you have a aluminum, whatever material, you do a tensile test, you have this yield strength, right? That's a yield strength 200 megapascal. And you subject these parts, okay, hydrostatically, and it doesn't feel, okay, it doesn't feel at a 200 megapascal. It will probably feel at a much higher value than 200 megapascal. That's the phenomena that noticed by this stressed by hydrostatically thing here. Okay, yeah. So this phenomena basically causes people to think is, well, maybe, okay, the parts or the material feel, okay, or yielding, okay, the yielding phenomena, it's not just a simple tensile, okay, or compressive phenomena, okay. It's probably more related to this angular distortion, okay, of this stress element, okay, angular distortion, right. So that's actually kind of makes sense, because why? When you apply the stress not so even on each side, then what happens is you create this distortion of these elements here, right? Yeah. If you apply it even on each side, then it's gonna basically, right, the volume will expand at the same time, and so basically, actually the volume, if you apply it evenly, will the volume change? Actually, the volume won't change, yeah, if you apply this stress hydrostatically, okay, yeah. So here's basically the sort of conclusion here. The failure, okay, the yielding, okay, more due to, okay, due to this so-called angular distortion energy. Okay, angular distortion of the elements or energy. Okay, yeah. So this prompts people to look at this. Okay, so then let's look at this, the so-called angular distortion energy in the stress elements here. Okay, yeah, in the stress element. Let's look at what's the angular distortion energy here. So this is basically the definition of the distortion energy theory here. Okay, so let me write down the definition here. Okay, and then we'll look at the formula. So the definition of the DE theory is basically says failure, okay, occurs, okay, failure occurs when number one quantity, distortion energy, okay, when distortion strain energies, okay, when distortion strain energy in the material, okay, exceeds, okay, the second quantity exceeds the distortion strain energy, okay, in a tensile test specimen at yield. Okay, that's the second quantity. Okay, very similar comparison mechanism to the MS theory, right? But the wording or the two quantities that they're comparing are absolutely different. Okay. So the definition, let's read it again here. Okay, DE. Failure occurs when distortion strain energy in the material exceeds, okay, this is the first quantity, exceeds the distortion strain energy in the tensile test specimen at yield. Okay, so now let's figure out the mass expression by first find out what are the two quantities here. Okay, what are they? Okay, so looks like we need to figure out the distortion strain energy concept here, right? Distortion strain energy. So to figure out the distortion strain energy, we have to look at two things here. Number one, we have to look at what's the total strain energy. Okay, total strain energy. And then number two, we're going to look at the distortion strain energy. Okay, yeah. So here is an illustration here. There is a lengthy derivations here. So I'm going to illustrate the process of finding this formula here. Okay, yeah. So let's say, suppose that I have a stress element. Okay. Okay. Suppose I have a stress element. Now I'll draw this principal normal stress only. Okay, yeah, principal normal stress. Okay. So any stress element will present a set of three basically principal normal stresses. All right, yeah. So for this particular situation, okay, or for any basically general state of stress, for any state of stress which produce three principal normal stress, you can always resolve this thing here into two parts. Okay, one part is basically, okay, you can always resolve it in two parts. One part, okay, so one part is what we call hydrostatic component. Okay, so which means every side of this element are subjected to the same value of stress. Okay, stress. So this component is called hydrostatic component. Okay, yeah. And the other component, and that's the other component is the component that will contribute this distortion energy. Okay, strain energy. So very easily you can see now, okay, so if sigma AV is a component of sigma 3, this is 2. If sigma 2 at here, so this will be sigma 2 minus sigma AV here, right? And this will be sigma 3 minus sigma AV. This will be sigma 1 minus sigma AV. Okay, yeah. So for the second component here, the three things are not necessarily the same value now, okay? So the second one here is what we call distortional component. Okay. Part doesn't matter. Okay. Yeah. So this is basically the model, okay, where the following equation will be derived here. Okay, so I'm not gonna derive this in here, just kind of to show you what happens at here. First of all, okay, when the in general, okay, when you have three principal normal stresses at here, then the total strain energy for this particular case, okay, the total strain energy, we'll use a U to represent the total strain energy. And that's 1/2 sigma 1 epsilon 1 1/2 sigma 2 epsilon 2 and 1/2 sigma 3 epsilon 3. Okay, so that's U for this one. So this is the total strain energy here, right? See, epsilon 1 and 2 and 3 are the strains, the strain caused by sigma 1, 2, 3. Okay, 1, 2, 3. And for these two at here, I'll use the UAV to represent this strain energy, okay, in the hydrostatic component. I'll use this UD to represent the distortion strain energy in this component here. Okay, yeah. So which means the total U will equal to this UAV plus this UD. Okay, plus the UD. Okay. So the UD at here is that distortion. This distortion strain energy. This is the quantity we're looking for. Okay, this is the quantity we're looking for. So basically, what does this quantity equal to, right? So if you look at this theory here, you're looking for this distortion strain energy. Okay, you're looking for two kind of distortion strain energy. One is what existed in the current state of stress. The other is what's the value in the tensile test specimen at yield, right? Yeah, that's the logic here. Okay, so I'm gonna skip a few steps at here as to how this is gonna be derived, but either way, so the process is you have to find this one first. Okay, find this one first. Find this one first, then use the U, subtract that, you'll get the UD. So that's the process as can be illustrated in the lecture notes. Okay, yeah. So in the end, okay, if you follow the process, it's not very hard, but not very bad. Okay, not very bad derivation, but I'm gonna skip that. We'll be able to find this UD value as this. Okay, so 1 plus V over 6E. So V is the Poisson's ratio, and E is the Young's modular. Okay, yeah. And then there is a very long expression at here. So sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, so that's UD. Okay, that's UD. So this is the distortion energy. Okay, distortion strain energy in a generally stressed element. Okay, in a general stress element. It's related to basically to the three principal normal stress, Poisson's ratio, and Young's modular, right? Yeah. So this quantity basically is this quantity. Okay, it's this quantity here. Okay, this quantity, right? Yeah. So we're comparing two things. So now we find this guy here, and we need to find the second one here. Okay, the second one. What's the second one here? Second one says this. Second one is distortion strain energy in a tensile test specimen at yield. So basically, the second one is actually the special value of the first one, right? Special value. Why special? Basically, that's the value for tensile test specimen at yield. So let's look at the UD. Let's look at the UD. What's the UD for a tensile test specimen at yield? Okay, so what does this UD for this tensile test specimen at yield equal to? Okay, so let's figure out this quantity. If we figure out this quantity now, then we basically have our DE theory. Okay. So for a tensile test, okay, at yield, okay, then I actually basically get back to the basic tensile test. So when it's yielding for a tensile test, what is the value of sigma 1, sigma 2, and sigma 3 under this situation right here? Right. So you need to draw a mole circle first. Okay. and then look at the mole circle. So for a tensile test, basically this is a tensile test, right? It's tensile test. Okay. Yeah. What's a stress element? Stress element basically there's nothing else but sigma, right? For sigma. Okay. At the yield, meaning the sigma will equal to what value? SYT, right? SYT. Okay, at the yield. So in other words, the sigma 1 will be, so let me draw this mole circle here. What does this mole circle look like? Right, that's the mole circle, right? That's the mole circle. So then that tells us was basically sigma 2 and 3 are both. What are sigma 2 and 3? 0. And sigma 1 will be SYT. Okay, so that's the value sigma 1 to 3 for this situation. Okay, for this situation. Okay, then things are easy now. You're looking for the UD based on these values here. So what do we do? We basically substitute this over here, right? Over here. Okay, over here. So then this quantity, substitute these 3 over there. So what do we get? We get 1 plus V over still 6E, but well, let me write it down here. Okay. Yeah, so you plug this into here, that's SYT square. You plug these 2 here, that's 0. You plug these 2 over here, that's SYT square. So they're 2 SYT square, right? 2 SYT square. So these 2 cancel 1, 6. There we go. That's the UD. That's the distortion strain energy for a tensile test specimen at yield. Okay, at yield. Is that clear? Yeah. So then the next job is, well, we want to compare this quantity, right? So we compare this quantity with what? With this quantity. Okay, so you compare these two. If this quantity is greater than this one, then you have a failure. If this quantity is less than this one, then you're safe. Right? That's what happens here. And fortunately, there are some common things between these two quantities, so we can simplify a little bit. Right? So when you compare these two here, so what does that give us? So this one compared to this, so this 1 plus V over E, this is 1 plus V over E, they're all going to be gone, right? They're all going to be gone. So what we end up with, basically the idea is the DE theory can be rewritten now. Okay, the DE theory can be rewritten as the following mathematical expression. So basically it says failure when what? When this quantity compared to that quantity, basically when sigma 1 minus 2 square plus 2 minus 3 square, 3 minus 1 square, okay? When this quantity is greater than 2 SYT square, okay? So that's the DE theory now, okay? So we don't have to worry about the Poisson's ratio and the Young's modulus, or the stiffness. Okay, so this is not the conventional way of writing this DE theory. So people keep going just one more step here. Okay, so this is equivalent to say that move this 2 to this side, and then take a square root of both sides of this equation. So we have basically something over here over 2. Alright, so what we're comparing now, okay, is instead of these two quantities, we're comparing these two quantities here. Okay, these two quantities. Okay, yeah. Okay, so this is quantity yield strength, right? So basically you're comparing something with the yield strength. When it's greater than the yield strength, it's failure. When it's less than that, it's okay, right? It's okay. So the this side here, okay, this side, okay, is defined as a new symbol here, sigma prime. Okay, sigma prime. So essentially now you're comparing sigma prime with SYT now. Okay, SYT. And the sigma prime is named after the discovery author of this theory. So sigma prime is called von Mises stress. Okay, so this one here is called small v and von Mises stress. Okay. If you do any stress analysis using any CAD software, okay, one of the theory, okay, most probably, and not the most 100%, you will have one of that is this D theory, and one of the plots that's going to give you is this von Mises stress. Okay, so it shows you the distribution of this von Mises stress across a certain part of different locations, right? Yeah. Okay, so that's DE theory. And in terms of analysis of design using this theory, and it's actually the same way of using it. So what we do is we looking at the safety factor between SYT and sigma prime. Okay, so this is a safety factor here, right? The safety factor. If this is less than 1, then it's unsafe. If it's greater than 1, then it's safe. Okay, safe. Okay, any questions? All good? Yeah, so I'm skipping one details here, but I do need to basically know absolutely this portion right here. Okay, yeah, what is DE theory? Yeah. You should also kind of have some ideas of where this is derived based on the distortion string energy. Okay. Okay, so this is a formula in terms of a sigma 1, 2, 3, which is the 3 principal normal stresses, right? This is the formula here. Okay, but if you recall that in most of the cases, what we deal with is plane stress. Okay, plane stress. So dealing with plane stress meaning you only have what? You only have sigma x, sigma y, tau x, y, right? So that's the plane stress. So there are a couple of different versions of this software, this equation now, this formula. Okay, so for the first, okay, for the first version of this one here, so let's see. Basically, we're looking at DE theory for plane stress. Okay, for plane stress. Okay, so for plane stress means you only have sigma x, sigma y, and tau x, y. Okay, or you only have that sigma A and sigma B, the 2 principal normal stress calculated based on that traditional formula. All right? Yeah. So then I've skipped the derivation. So then your sigma prime. Okay, you see the sigma prime von Mises stress. Von Mises stress is calculated based on this formula here. Okay, based on this formula. And when you have a plane stress, okay, when you have plane stress, and one of them will be 0, right? One of them will be 0, and the other two will be sigma A and sigma B. So you can easily get a different version of formula, and that's root at here, sigma A squared, sigma A sigma B plus sigma B squared. Okay, so that's a different version of DE or von Mises stress. Okay. Now, if you don't like to use this one, you have the third option. And that option is to express sigma prime using sigma x, sigma y, and tau x, y. So how do you do that is, remember what sigma A, sigma B is, which is this, right? Which is this, okay? Which is this. So if you substitute this one over here, okay, and you do a little simplification, you will get this one. Okay, you'll get this one. Okay, so that's the third option here. Okay, the third option. Yeah, but remember, these two formulas only applicable when it's plane stress. Okay, plane stress. If you have a 3D stress, then you're gonna have to rely on this formula here. Okay, this formula. Okay, so all good. Okay, so lastly, graphically showing this DE theory. Okay, DE theory. So the graph will show, essentially, we'll just use the graph to show this plane state of stress that is here. Okay, plane state of stress. Now, the same kind of approach as we did in for the MSS theory. So what we do is we look at a plane created by sigma A and sigma B. So then, if I look at this DE theory, so what the DE theory basically comparing is sigma 1 prime versus SYT, right? This is what DE theory is being comparing with. Now, if I pick this equation here has nothing else but sigma A and sigma B. So I'm gonna let this equation equal SYT. That's the boundary, right? That's the boundary. So if you let sigma A minus plus this, so if you let this equal to SYT, then this chunk equal to SYT squared, right? SYT squared. So this is basically the boundary. Boundary here. Okay? The boundary will separate the safe and unsafe region. Okay? So the next question is, we're going to plot this thing in the sigma A and sigma B plane, because it's like XY plane here, right? XY plane. Okay. So fortunately, we don't have to plug in points because we know that from a mathematical point of view, we know that this is actually basically an equation representing an ellipse. Okay, representing an ellipse. So this is an ellipse. Okay, equation. Okay, ellipse equation. And this is an inclined ellipse here. So what happens is, what you see is an ellipse looking like this, and a tilted egg. Okay, yeah. And this is the boundary describing this equation right here. And there are a couple of important things here. This point, okay, is SYT. Okay, this point is SYT. Okay, and same thing. That point there is negative SYT. Okay. And it's a symmetric. Okay, if you draw a line here, it's symmetric, and this line here is sigma A over sigma B. Okay, over sigma B. Okay. All right. So now, if I draw the MSS and this, the ellipse is not drawn very well, but what happens is you can sketch this DE theory, the locus, together with the MSS in one plot. Okay, you can sketch them in one plot. So technically, I don't think my drawing is not that good here. Maybe it should be a little bit fatter over here. It should be a little bit fatter. Okay, should be a little fatter, but I'll draw that later. Okay, I'll draw that later. Yeah, essentially that little thing, the hexagon here, essentially the hexagon for the MSS. Where is the hexagon here? This hexagon here is going to be inscribed inside that ellipse. So that ellipse, okay, more of like this. Okay, yeah, that ellipse is like this. Okay, yeah. So I'll draw that later. Okay, I'll draw that later. Yeah. Okay, any questions? Okay, all good? Yeah. Okay, so now let's look at a special case again. Remember in the previous example, we look at a special case called the pure shear line, right? Or the pure shear loading line. So let's look at this pure shear loading line again here. So this is the line, the pure shear loading line. Okay, pure shear loading line. So let's look at this pure shear. Okay, sigma A equal to negative sigma B. Okay, that's the pure shear loading line. And the intersection of this loading line with the boundary at here, okay, will give us the shear strength. Okay, will give us a shear strength. So this point here is very critical point here. So let's solve this line with this equation, right? You can solve this line with this equation. Okay, so I'm not going to solve, but it can be easily solved for these two lines here. So when you solve this thing here, so what happens is, okay, so what happens is you can do this, all right? You can do this. Pure shear is this, right? Pure shear is, okay, nothing. There's no normal stress, but this shear stress. That's pure shear. So when you have a pure shear here, which means the sigma x will equal to sigma y equal to what? 0, right? Equal to 0. Okay? Yeah. And we're solving the intersection point at here. Now, the boundary can be represented by this equation. It can also be represented by this equation here, right? You see that? Right? It can also be represented by this equation. So I'm not going to use this one. Maybe I should use this one because I already have sigma x equal to sigma y equal to 0. So I'm going to plug it here. I don't have anything else but this now, right? But this now. Okay? Yeah. So which means the sigma prime becomes root 3 and tau xy. Right? Does it make sense? So if I substitute 0, 0, 0, so this is not square here, right? It's going here. It's not square. Minus this plus sigma y squared, right? So there's nothing else, not just 3 this and root 3 tau xy, right? Root 3 tau xy. Okay? Yeah. So that's your sigma y prime. And your sigma y prime, your sigma prime compared to which one? Compared to the SYT, right? Compared to SYT. That's the D theory. If this is greater than that, you have a failure. If this is less than that, you're okay, right? So then the equal sign represent is the critical point, right? Critical point. And the equal sign here give us a special value tau xy, right? So the equal sign give us special value tau xy. And what is the special value of that? It's SYT over root 3. So it gives us this special value. Okay. Why is it special? Because anywhere beyond that it's failure, and less than that is good, right? Yeah. So this tau xy, and that's the tau xy, the value under pure torsion, and the pure torsion supposed to give us a test value, supposed to give us a shear strength. So this special value is the shear strength value that we're looking for. Okay? So now, if you calculate this 1 over root 3, you will see that this is equal to 0.577 SYT. Okay, 0.577 SYT. Okay. So remember, what's the shear strength value based on the MSS theory? What's the shear strength value, or what's the SSY value based on the MSS theory? It's what? 0. What was the MS? So for MSS, what is the SSY value? 0.5. Right? 0.5. So in MSS value, you are comparing the maximum shear stress with this, with the MS with SSY here. In this one here, your shear strength is 0.577. That's one. So tell me which one's bigger. So which one, which give us a which one has a bigger shear strength value? Which theory give us a bigger shear strength value? DE, right? So DE has a slightly bigger. Okay, so here's the idea now. So DE is you're comparing with a bigger strength value, right? You're comparing with a bigger strength value. But MSS is you're comparing with a slightly lower, a smaller shear strength value. So technically speaking, see this is basically generally what we do, right? You're developing a theory, and you wanted to compare with this one, and he's developing another one. He's comparing to this one, and he's smaller than yours. So tell me which one is more conservative, or which guy is more conservative? MSS, right? MSS. Okay, yeah. So basically, this is basically means it's slightly conservative here. Okay, slightly conservative, right? Yeah. The conservativeness actually can also be explained very easily based on the graph there. So maybe I'll just draw the graph here. So for MSS theory, what we see is it's a hexagon here, right? It's a hexagon. It's a hexagon. And for DE, it's an ellipse, okay, enclosing, okay, this hexagon. Okay, this is DE, and this is MSS. Okay, MSS. So apparently, the MSS has a smaller safe region, right, than the DE theory. Okay, and the DE theory. In other words, if you have a point, if you have a state of stress somewhere here, and it's safe, right, according to the DE, but it's unsafe according to MSS here. That makes sense? Yeah. Okay. Okay. So any questions? No good? So we had enough theory here. So let's take a look at a couple of examples here. Okay. So we probably won't be able to finish all example, but we'll look at a more complicated example at the beginning of the next lecture. So first, let's look at a very simple example. Let's say I have a material, hot rolled steel. Okay. The steel has SYT value 100 TSI. Now I want you to use MSS and DE to calculate the safety factor based on the following loading condition. Number one, let's try this one here. Maybe just try one. Let's see. Number one, let's try this. Sigma 1 70, sigma 2 0, sigma 3 is this. Okay, KSI. Okay, let's try this. So for this loading condition or state of stress, what would be the safety factor based on the MSS and the DE? There's nothing tricky here. It's purely just calculation, right? Just pure calculation. So first, if I use DE, I need to calculate this von Mises stress. And von Mises stress is the formula, okay, 1/2 the big formula there, right? The big formula. It's purely calculation based on sigma 1. So you do the calculation, and you will find that it's equal to 88.9 KSI. Okay. And if I use the DE, then the next step is we compare. Okay, we compare this SYT with this von Mises stress. So SYT is 100. Okay, that's the calculation. So equal to 1.13. Right, so that's safety factor. So it's safe, right? According to E is safe. Okay, according to E is safe. Now, if I use this MSS theory, okay, MSS theory. So according to the MS theory, okay, the N equal to SYT over sigma 1 minus sigma 3. Okay, minus sigma 3. So sigma 1, sigma 3 is already given. SYT is over here. Okay. So the overall is 100 over 70 minus 70, so that's another 100. So it's 1. Right? It's 1. So according to the MSS theory, okay, MSS theory, what we have here is actually marginally stable or safe, but DE is still certain margin there, right? So margin. So this is actually another example showing that MSS is more conservative. If we look at the location, right? Let's see if I want to know where is that state of stress at here. Okay, where's the state of stress? So this, yeah, let's see. This might not be from a plane stress, but anyway, maybe it's from a plane stress. So which means this is my sigma A, and this is the sigma B here, right? It could be a sigma A and a sigma B. So basically, it's somewhere in this region at here, right? Somewhere in this region. And for MSS, it's right on the edge, but there's still a little bit of space at here to the DE boundary. Okay? Yeah. Yeah.
So does that mean which one's better over the other one?
It doesn't tell you which one is better or which one is. It basically all it tells you is based on the criteria you selected, what will be the safety factor. Yeah. So if you might work in an industry that that asks you to be more conservative, you use the DE at here, right? Sorry, the MS is here. But you might want to work in an industry that wants you to be more precise. Precise basically saying is that people did some experiment. They actually show that the DE, okay, are more precise in terms of approximating the experimental results. Okay, so that's why the MSS is more conservative. Just it's really there's nothing wrong in it here in terms of which one is or better or worse. Okay, so that's the typical calculation. Okay, you can look at some other things there in terms of calculation. But I wanted to cover the next one here. This is more of a so-called graphical approach here. Okay, so let's say you had a situation, right? Let's say I don't have a calculator, and I don't remember any formula now. Okay, yeah. So this is the kind of a Stone Age calculation here. Okay, yeah. So let's see. I give you a state of stress now. Sigma A is 100 megapascal, and sigma B is 80 megapascal. Okay, yeah. And let me give you another one. So same sigma A, slight different sigma B. Okay, yeah. And the material is AISI 1018 steel. Okay, so here is this thing here. Now they want you to analyze: is it safe, or what's the safety factor, right? So now this is the basic thing. You don't have the formula, you don't have a calculator. All you have is a ruler, right? Yeah. So then what happens? of course, based on the knowledge, you know how to do division, you know how to do multiplication, right? Okay, so this is what's going to happen now. So what we do is we look up the table and to find the material property. And for this material property, your SYT equal to 220 megapound. Okay, yeah, that's the property. And now we're going to use the graphic approach that we use the graphic approach or the safety region, safety graph, okay, for both theory. Okay, yeah. So let's use the MSS theory. Okay, this is sigma B, this is sigma A. So what you do is you do this. You're gonna draw this safety curve, the safety boundary for the MSS. Okay, so you're gonna draw this MSS safety boundary. So, but you don't draw it arbitrarily though, huh? You draw it according to scale. So the scale is according to this material property, 220 megapound. So then, and this is, you have the freedom here. So let's say, for example, right, you have the ruler. So we're gonna let 1 inch on the ruler, okay, to be approximately that 220 megapound. Okay, megapound. And 1 inch. So let's say you draw the 1 inch over here. Remember that MSS theory is hexagon, right? It's hexagon. So you draw the hexagon, and you know that the special value of the hexagon here is SYT. Okay, it's SYT. So basically, you use a ruler. You let this distance to be 1 inch, and you remember that 1 inch represents is 220 megapound. Okay, yeah. So finish that hexagon. Okay, yeah, draw it according to scale with the proper precision, right? Then the next step, okay, so draw. So this is, let's say, the first step here, okay? And then the second step is you mark the state of stress. Mark the state of stress according to the given value. Okay, so mark this state of stress. Okay, mark this state of stress. Okay, in the graph. Okay, so when you mark the state of stress, basically you're like picking a location, right? According to the coordinates. So then here you had to do that according to the precision that you did. So for example, this is 100 megapound, right? This is 80 megapound, right? So sigma A is roughly half of this SYT. So according to the scale that we done, half, it's a little bit less than half, but that precision you have to be there definitely gonna be a little human errors here, right? Yeah. So this is gonna be the sigma A here, right? Sigma A here. Whereas B is 80. So 80 is still smaller than half of that, so it's probably somewhere here, right? Probably somewhere here. So use your ruler and nail that as precise as possible. So that's the point. Let's say this is, I'll use the point A here for that state of stress. Okay, for that state of stress. So once you've done these two steps now, then the third step, okay, is you draw a load line. Okay, you draw a load line by connect OA. Okay, O is the origin of this coordinate system. Okay, so this is O at here. So draw it. Okay, and extend it. Okay, that's your load line, right? That's your load line. Okay, yeah. And this load line will intersect with the MSS safe boundary at a point. Let's call that point B. Okay, let's call that point B. Is that good? Yeah. So maybe write down here. Draw the load line and find B point. So this is intersection with boundary. The last step is to use your ruler to calculate the safety factor. So the fourth step is, okay, measure OA and OB. Use your ruler to measure it. Okay? Yeah. Then your safety factor is OB over OA. Okay? So measured it, okay, and safety factor is OB over OA. Okay, that's the graphical approach. So if I do this one here, so I'm not I don't have a ruler here, right? But you can try it out, and you get a pretty close one here, pretty close value to the actual. Okay, yeah. So for this one here, you probably get a 2.13 as I did in my on my own paper. Okay, so that's your approximate value. Your actual value, your actual safety factor, if you remember the formula, it's going to be the SYT, right, 220 over sigma 1 minus sigma b, sigma 1 minus sigma 3, and you're at the first quadrant, so it's actually just divided by 100 sigma a value, so that's 2.2. Okay, so pretty close. Okay, pretty close. Yeah. So if I coming back here, so you need to basically look at the MSS theory, right? MSS theory, we had three different cases. One case is when you over here, here, or here, and how would you calculate the safety factor, right? There's different three different formulas. Okay. However, for the first one here, when you calculate safety factor, okay, it's actually just SY value over sigma A. So for this region, it's N equal to SYT over sigma A. Okay, over sigma A. So now let's look at middle school geometry here. Okay, so if I connect, right, this point has a coordinate sigma A, right? Coordinate sigma A here. So you connect this, but that's the point here. So now you look at this triangle here, right? Look at this triangle. So what's the high school thing here? Similarity. Well, OB over OA equal to this divided by this, right? And which means OB over OA equal to what? SYT divided by sigma A, right? So that basically validate how the safety factor N here equal to OB over OA. Okay, yeah. Is that good? Yeah. Okay. Now I have another point here, sigma A, sigma B, 140 here. So if I plot this 140 on the graph right here, so 40 is half of the sigma B. So your second one, let's say this is the E point here. Let's say the E point. Where would that be? That will be here, right? That will be here. Okay, in the middle of this point. So this is the E point here. This is the E point. If I do the same approach, I draw a load line and intersect, okay, here, and the safety factor, let's say this is F, it will be OF over OE, right? OF over E. Okay. So if you pay attention to what I just said about the way you calculate or how to validate this this way of calculating safety factor. What would be the safety factor at this point E? Should be what? The same as the safety factor at A, right? Yeah. So geometrically, you say OF over OE is same as OB over OA, right? Yeah. So that's actually one of the advantages of this safety factor. Many times you can easily tell of approximately what the safety factor of that point is. Okay. Yeah. Okay, so we still have a couple minutes here, so not new example, but let's stay on this approach right here. Okay, still on this approach. How about I'll give you a different ones here. Let's say if I have sigma A equal to 100, but sigma B is negative 40. Okay. So how about this guy here? So if I use the same approach, okay, I use the same approach. Sigma A is the same value, still at 100. But sigma B is negative. So basically right now, where are we now? We are not in this quadrant anymore, right? We are somewhere here, right? Somewhere here. So same magnitude, it will be this location, right? Be this location. Let's call that C location. Okay. So now this is the state of stress according to the sigma A, sigma B value. Okay. Then if I want to calculate the safety factor, so we can do the same thing. We draw the load line, okay, connecting OC, and that'll be the D point here, right? That will be D point. Okay. Yeah. So for this particular case, your safety factor will be OD over OC, right? OD over OC. What's going on? So that means class is over. Huh. Okay, so anyway, so let's just leave it as it is. I don't know. It's just the good thing is we're not too bad. Yeah. So I'll see you next week, and I'll give out the first assignment this Friday, right?